I'm Larry Posnikoff. I'm with the Technical Safety Authority, and I'm here to run through what a basic inspection might entail on a traction engine in Saskatchewan. We're at the Western Development Museum. This is a prime example of a traction engine boiler. It has basically been a welded replica boiler, but still it has all the same features of a riveted boiler. On an inspection, what we are generally looking for is the condition of the boiler. There will be several different types of inspection. The first initial part is what I'm going to go through right now, because we are not at a point where we can demonstrate a hydrostatic test on the boiler or an operational inspection on the boiler. When I arrive at a location, one of the first things I do is to look at the general condition of the boiler. I look at the identification, if there is identification for the boiler, and generally go around to see if there is anything visibly evident missing on the boiler as I find it. I'm looking for the safety equipment. This boiler at the present time is in a cold, dry layup state. So the safety valve has been removed from it. The boiler has been drained. The handhold doors have been opened and covers have been put in so that it can be kept dry, and it has been washed out. I would ask the owner to see the safety valve. It has to be tested yearly, and it has to be sealed and stamped by a registered company that does that sort of work. Steam gauge, I believe, has been put away because it also would be susceptible to possibly frost or maybe even vandalism in certain cases. I would also check to see that the gauge was in good shape and was calibrated to the operating requirements of the boiler, which means that the operating range of the gauge, so where the boiler is being steamed to, is at in the top third of the gauge. Typically it'll be somewhere around the top. For instance, if you're running a boiler at 200 pounds, the gauge would be a 300-pound gauge, and the operating range would be in the center of the gauge. I would check the valves to make sure that all the valves have appropriate ratings on them. Check to make sure that there's tri-cocks and a gauge glass, and that they're all appear to be in good working condition. This could be further checked during the operational inspection once there's water and steam, to make sure that they aren't leaking and that they actually work the way they're supposed to be working. Flywheel is one thing. Flywheel is very important because it is the balance of the engine. It has the potential of cracking or breaking if it's mistreated, held on with a pin. It could fly off. If that happens during a demonstration, somebody would get injured. So do a good visual inspection, make sure there's no chips, cracks, or any other damage to the flywheel. Other areas that are addressed are things like the other mechanical pieces involved with the steering. If these areas are broken, even under normal condition, if there's evidence of cracking, breaking, missing parts, it could cause a catastrophe if it was to fall off its steering. That does happen from time to time. You'd look at the axles and the bearings and that sort of thing. The linkages where they're attached on, you look for general cleanliness on the top of the boiler. Very often there will be different materials that will fall in, either ash, oil, dirt will fall in on the wing plates. That's the engine mounts, and they will rest between the boiler and the wing plate, and that can be an area where you can have external corrosion happening. You would also be looking at the governor to make sure that all the pins and everything are good on it. Another piece in motion that has the potential for causing massive injury. You look at the seams to make sure there's no external corrosion or damage, and basically mounts for different wheels or different parts of equipment. One of the things that most people don't look at very often is there are dampers. We cannot see the damper on this one because it's at the back, but it is just a flap cover for allowing combustion air into the fire. If it doesn't seal properly, you can't control your fire properly. This causes a firing issue, and so you check for a condition there. Ash pan, if the ash pan has holes in it, then it could cause fires. You want a good ash pan. Tight seal on your firing door so that you can control your combustion. That is the type of external inspection we would do on an engine like this. So the soft plug or fusible plug, it goes from the firebox side through the crown sheet into the water side of the boiler, and it is to be removed, it's to be cleaned, it has to be stamped. This one has been taken out, so it is put away. A new one will be put in this following year. I have a look at the threads where the fusible plug screws through, and make sure that they're in good condition. I would use my mirror and my flashlight and possibly a scope to look at the inside of the water side to look for evidence of heavy corrosion, maybe deposits of scale that haven't been missed during the cleaning. Make sure that everything is sound insofar as the weldments on this one, but in the case of a riveted one, there would be the threaded stays. And then there are stays all through the water leg. They're called stay bolts very often. On the older units, they're threaded all the way through and then upset on the ends to make a seal. They hold the sides of the water jacket, the water leg apart. We've taken the inspection to a cutaway. This is not an operating boiler, but because it's cut away, it allows us to see the inside, the water space of the boiler itself. By doing this, we can show the things we look for. If you look at these threaded stays, you can see the stays themselves. The threads are quite evident. They're in good shape. They're not eaten away. You can see that they've been threaded so that they can be threaded through. So these are called crown stays or radial stays. They are on the radius between the wagon top and the crown sheet, which is the top of the firebox. They are a threaded stay bolt, the same as these ones, which are between the firebox and the outside jacket. So these are the water leg stays, which are threaded stay bolts. These are called through stays. They are longitudinal stays that go from the back head and would continue through the whole boiler. Now this one's cut off at the barrel, but they would go right to the front tube sheet. These ones go all the way through. This gives us a chance to have a really good look at what they look like from the inside. It also, these through stays have washers. They're threaded through, and they have nuts to seal and retain the stays on the back head. This one does have some pitting on one of the major through stays, and what was asked was that they measure how much pitting is taking place. Inside, you can see the through stays going by the radial stays. There is visible corrosion on the stays, but it is not enough to warrant the removal of the engine from service, but it is something to be aware of. Record the depth of the pits on it and measure so that you can tell if there's continuing corrosion taking place to the stays. I'm looking at this, I'm thinking that it is not going to be an issue. One of the things with these engines, of course, is that they were rated at 150 psi and they're only being run at 100 psi. To do the calculations on the thickness required in the stay, you would find that even though these are wasted, they are not wasted beyond use. Look and see down into the water legs on either side. This light has a magnet in it. Very often you can get an idea of what kind of deposits there are by reaching in with your flashlight, and you can see that there is a fair amount of scale deposit in here. That would need to be cleaned out. That tells you that there is some deterioration happening. It's probably very minimal because this boiler has been treated, and that would indicate that the surface of the metal has set up an oxidation process, but it's a controlled, checked oxidation process that prevents further corrosion. The entirety of the firebox, if you would typically have the grates and the ash pan removed so that you could physically crawl up into the firebox and look very thoroughly at all the stay bolts, look for distortion, look for pillowing, look for the condition of the tube ends to see if they've been put in place properly, if they're tight to the tube sheet on the inside. Look to see if there's any cracking or any leakage visible from the tubes. That will happen from time to time. We would look at the general condition around the firebox. This one here, the bezel has been removed, but there's a casting that goes around. And one of the things we look for is ashes. There is evidence that there was some corrosion where the ashes sat in around the bezel. So that would be another area that we'd look at. Then you can move to the other end, the smoke box end, the hand door openings, to make sure that they haven't corroded or eroded to the point where they are not going to seal properly, and that there's enough material holding the pressure element in. As I was saying, you check to see the thickness of the opening for your hand door. This is a hand door. This is the hand door gasket that seals up on the inside. I would also check to make sure that all the tubes are properly beaded up against the boiler. There should be no space in between rolled bead on the tube and the tube sheet. These ones are all good. I would check to make sure that it had been cleaned out properly. This one appears to be cleaned out properly. If we come to the side here, there's an observation port. This was an area that's used for looking at the tube ends. This one has evidence of ashes being left in over the winter. The problem with leaving ashes in is that there can be external corrosion. The ashes act like a sponge and hold the moisture close to the boiler. This could lead to deterioration to the point where the boiler needs repair. This particular welded boiler was made in such a manner that that ash would not actually affect the surface of the boiler, because there's a standoff plate and the ash is collected between the standoff plate and the boiler shell. So dead center is a term for when the piston reaches the end of its stroke. If momentum is lost, the engine will stall. It creates a dangerous condition because there is a small charge of steam that acts as a cushion at the end of the stroke still in the cylinder. If you don't remove the steam supply and drain the cylinder, then there's stored internal energy that will cause the rotation of the engine, which, when an operator is moving the flywheel to put the motion back in the machine, will cause him to be thrown over the engine and do grievous damage to his body. Typically, there are two places on a simple single steam engine. That's an engine with one piston, and that drives in a double acting motion with steam being admitted to both sides. The way the steam is admitted is through the sliding D valve. There are several terms that are used in conjunction with this steam action. There is the lap, the mount that the edge of the sliding D valve closes over the valve port when the admission is stopped to the piston. Admission means that live steam is being actually admitted into the cylinder itself. There is the lead, which is the amount the valve is open for steam to be admitted at the end of the stroke to create the cushion. And there is the cutoff, which is the point at which the valve is completely closed and the steam expands to create the motion. The cutoff is considered to be a economy feature, which means that they call it hitching the gear. You could set the gear so that more live steam or less live steam was admitted to the cylinder for power, and less, of course, less steam for economy, because the less live steam being admitted and more expansive steam being used meant greater efficiency, greater economy. This is a triple riveted lap seam. The distance between this rivet head and the edge of the plate here is the same distance between the inside sheet and the rivet head on this side. The lap seam is a seam where they take the single sheet of steel, wrap it around, and overlap the seam one side on top of the other side. So this comes over top strength. And this one, I think, is around 65, they call it a 65% joint efficiency on this. So this would be one of the stronger, well, it is the strongest lap seam that they made. Boiler is a Canadian made. This one, instead of having the sheets overlap themselves, they butt the ends of the sheets together. They put a reinforcement plate on the inside, which would be just past the rivets on the outside of this outside reinforcement strap. There are 3 rows of rivets on either side of the seam, and so this is a triple riveted butt strap boiler. This would be about 85% joint efficiency.